Alright, welcome back. We're going to look at another theorem that's useful, although I should say it was useful before there were calculators. It's worth noting, even though, what you'll be responsible for is just the basic idea of it and maybe applying it on a basic level, and that's about it. Okay, so let's just look at this problem. It says find all real zeros of this polynomial. So I want to keep in mind, this is the thought process you want to go through when you're asked a question like this. First of all, can I factor it? Because if you can factor it, that takes the least amount of time, and that's what you try to do first. Now, if you look at this is a degree 3, so the only technique we've learned to factor this without like any other information is factoring by grouping, which would mean that you can you put parentheses around these two sections to group, and you see if you take out greatest common factor. So in here you take out x squared, and you'd be left with a 2x minus 7, and here you have a 2x plus 3. Now this doesn't help me because what would have to have happened would be that this would have had to have been the same as this. If you look back at the factoring by grouping notes. Now that didn't happen, so it doesn't look like factoring by grouping is going to help us. We don't have a calculator on us. So what do we do? Well, if you think about the last video where we looked at some of the useful theorems, if we can find 1 0, right? If we can find 1 0, then we can do synthetic division to get the other ones, right? So if we could only just find 1 0, that would be enough to get the ball rolling. And so this theorem helps us do that, the rational roots theorem. So what the rational roots theorem says is, I'm just going to pull it over here, and you can copy it down. It says that if a polynomial has a rational 0, it is of the form factor of constant term divided by factor of leading term. So let's decode that for a minute. First, let's look at this word rational. So rational numbers are numbers that can be written as fractions. So for example, 4 is a rational number, 1/2, 0.7, right? Because 0.7 is the same as 7/10. Those are all rational numbers. Irrational numbers are numbers like √2 and pi. So we're talking just about these guys. Okay, so it's called the rational roots theorem for that reason. Those are the type of zeros you can find. The other thing is the factor of the constant term. Well, the constant term is always this one at the end. That's the constant term. And that 2 is the leading term. Okay, so what this is saying, this theorem says, if there is a rational 0, and sometimes there isn't. You can have irrational zeros for a polynomial. We won't get into that now. But if a polynomial has a rational 0, it is of the form a factor of 3 divided by a factor of 2. That's the form it takes. So let me show you. I'm going to move this definition. I hope you copied it down. I'm going to move this definition to the side or in the trash for now. And we're going to do this example. We're going to do this problem out. Okay, so I'm going to write down now. I'm going to generate the possible rational zeros. By the way, zeros and roots, we kind of use them interchangeably in this unit. Possible, I'll just write zeros. So this is how you generate them. According to the rational roots theorem, if you look back at your definition, they are of the form the factors of the constant term. So the constant term is 3. So what are the factors of 3? Well, 1 is a factor, and so is -1. So I'm going to put a plus or minus 1 here. That's just short notation for 1 and -1. There's 2 numbers there. And then other factors of 3 are plus or minus 3. Positive 3 and negative 3. Okay, right, this is the factors of 3. Factors of our constant term 3. And then we got to divide that by the factors of the leading term. So the factors of 2 are plus or minus 1, right? 1 and negative 1, and then plus or minus 2. And again, these are the factors of the leading term, 2. And so what this generates is we've got to now sort of look at, this is kind of shorthand notation for a bunch of numbers. We got to take all combinations of numerators divided by denominators. So when you take a plus or a minus 1 and divide it by a plus or minus 1, the possibilities you can get are 1 and a minus 1. So I'm going to write a plus or minus 1. A 1 and a negative 1 are the possibilities you can get when you do this division. You could also do plus or minus 1 divided by plus or minus 2, which is plus or minus a half. That's it for the 1's on the top. Let's try with the 3's on the top. Well, plus or minus 3 divided by plus or minus 1 results in a plus or a minus a 3. And then you could also do plus or minus 3 divided by plus or minus 2, which gives you a plus or minus 3 halves. So look at, this is the list of the possibilities. And there are 8 numbers here. It looks like there are 4, but each one is a plus and a minus version. And so what the rational roots theorem says, we generated this list of possibilities. What it says is that these are the ones we should try. So what I mean by try is go back to the theorem we did earlier, the remainder theorem. If you plug in a 0 and you get, when you plug in a number or a possible 0, what you get is the answer is the remainder. So what we want to do is we want to plug these into the function and see which one gives us out 0 as an answer. Because as soon as we do that, we've found 0. Now, the natural thing, this can be a pain, right? It would stink if we did these in order, 1, negative 1, 1 half, negative a half, and the one that worked turned out to be 3 halves or something. That would be annoying. Just so you know, like the ones you'll come across, we set it up so that the ones that work are generally, the easier ones. So we're gonna start by plugging in 1. So actually, to be honest, you can plug in 1, right? Oh, well, yeah, let's do that. We're gonna plug in 1. So f of 1, and what we're interested in is we're hoping this turns out to be 0, so that we can just go ahead and continue doing synthetic division and then factor and find the zeros. So this equals, that's 2, right? 2 times 1 cubed is 2, minus 7 plus 2 plus 3. And what do you know? This is negative 5 plus 5, so this is 0. Excellent. So we lucked out. We lucked out because the first one we tried worked. As soon as you find one that works, and again, it could have been possible that one didn't work. We could have gotten not a 0 as a remainder, and then we had to try another one of these. We would have had to have tried like negative 1. And then we keep going until it works. Okay. But now once we know that 1 is a 0, that's what this means. 1 is a 0. To answer the question, it says find all real zeros. Let's just keep track of them over here. We'll leave our answer is going to be here. We found one of them. One of them is 1. To get the other ones, well, let's do synthetic division. I'm going to put 1 in the box, and I'm going to copy down the 2, the negative 7, the 2, and the 3. Bring down the 2. Now, by the way, I know I'm going to get 0 here, right? Because I just confirmed that above using the remainder theorem. And I did. And so what this means is, we're sort of, we're really factoring this, but we're just keeping track of the zeros. This division here really means that when I do 2x cubed minus 7x squared plus 2x plus 3, if I divide by x, now the factor associated with a 0 of 1 is x minus 1. So what it means is I can divide that up into x minus 1 times 2x squared minus 5x minus 3. And now, I know the 0 associated with that. We already got that one. Now I just have to look at this and factor this if possible. And I think it factors nicely. 2xx, 3, 1. I think that works. Check that. And so the 0 associated with this term is negative 1/2. And then 1 associated with that one is 3. And so there we go. I got all my zeros. Right, I got all my zeros using synthetic division. But the key, what's new to this is that what got the ball rolling was this theorem called the rational roots theorem. So you really want to know how these numbers were generated. That's what you're responsible for. Okay, mainly that's what you're going to be responsible for. I'm not going to emphasize this so much because if you have a calculator, it makes more sense to just put the thing in your calculator. Okay, but make sure you know how these are generated. Make sure you know what it means to test them and how to use the theorem to get the ball rolling and then find the zeros.